Aloha Kakahiaka. Team RoSE has returned to the University Rover Challenge with its 5th iteration of the emulated Mars rover, improving upon shortcomings observed during the team's performance in June 2025. Our mechanical, software, and hardware systems have been completely overhauled to improve team performance for the 2026 URC Finals.
Our suspension is a rear-mounted differential bar driven by neo-vortex motors featuring custom gearboxes to balance speed and torque. To handle intense shear stress and bending moments, we utilize A1011 steel gussets paired with 6061 T6 aluminum tubing for high rigidity at a minimum weight. This architecture provides 14.5 inches of ground clearance, allowing the bot to traverse 18-inch obstacles and 23-inch drops. Finally, our Michelin-inspired moon tires are mounted to custom PET-CF 3D printed hubs reinforced with steel gussets for maximum stability.
To address the dexterous demands of both equipment servicing and delivery mission, we designed a 5 degree of freedom robotic arm powered by multi-stage planetary gearboxes. With a combined 135-to-1 gear reduction, our gearbox stack increases torque from the neo-vortex motors to up to 94 Newton meters. The first 3 joints are directly driven for high precision and stability, while the final 2 joints are operated by a gear-driven differential wrist powered by Neo 550 motors with planetary gearboxes. This system delivers up to 77 Newton meters of torque in both wrist axes, enabling fine manipulation and precise orientation control. A high-load cross-roller bearing at the base joint supports forces up to 20 kilonewtons, ensuring structural rigidity during operation. With this design, the arm can safely lift payloads of up to 5 kilograms within a 10 centimeter operation width. For accurate manipulation, the end effector features a linear actuator, enabling precise vertical motion for tasks such as typing on a keyboard and flipping switches.
This year's rover implements a full autonomy localization pipeline using redundant sensing and sensor fusion. Inertial and visual data are provided by the Z2i, while dual ZF9R GNSS boards with RTK corrections deliver centimeter level positioning. On the drivetrain side, we publish real odometry from encoder feedback. Sensor data is fused using an extended Kalman filter in RoSE2 to the robot localization package, providing refined state estimates that are then used by the Navigation 2 stack to transform GPS waypoints into the rover's local frame while managing global planning, control, and continuous path correction. The Autonomy Perception System integrates the Z2i with a custom-trained YOLO V11 model for real-time object detection and the OpenCV Aruko library for Aruko tag detection and full 6 degree of freedom position estimates relative to the camera.
For our science mission, the payload performs autonomous subsurface sampling and on-site biochemical analysis. A lead screw actuator lowers an auger up to 10 centimeters below the surface to collect samples. The sample is transferred through a rotating funnel into O-rings sealed vials inside a carousel system. An integrated shaker oscillates them vertically to ensure a uniform mixture. We run 2 liquid-based assays. The first is Crescent Red with SDS. This mixture will change from a yellow color to an orange color as metabolic activity produces byproducts that lower pH, indicating life. The second assay is Bradford Regent. This will change from a brown color to a bright blue color as the stain reacts with life-indicating proteins. An internal UV and LED controlled camera monitors color changes in HSV space, measuring reaction, magnitude, and rate. We compare results against positive and negative controls, while temperature and moisture sensors log environmental conditions for a complete on-site biological assessment.
For drone reconnaissance, we utilize the DJI Mini and are currently working on a custom drone. The DJI Mini connects from the controller to a 2.4 GHz relay. The custom drone's electrical frame uses an iFlight kit that connects to the Betaflight software and can also use the relay. For communications, we use a dual 2.4 GHz and 900 MHz network, which utilizes Ubiquiti devices and various antenna to provide high throughput communication at long distances.
This year's battery is a 4S 8P design, giving us the same capacity with a lower nominal voltage and a higher amperage output. This necessitated us to change the BMS. Both the main and backup battery outputs are tested and can be quickly swapped via the battery module. Finally, the e-stop has been integrated into the back of the rover and can be easily pressed to disable the battery.
This year's chassis addresses ARM and Science payload integration with one connection point on the front of the rover. The wires for both configurations are easily accessible and feature waterproof Deutsch connectors thanks to dedicated I/O panels. The battery and computational components are separated into removable modules for ease of transportation, testing, and development.
Team RoSE actively works with the community through outreach events, including Lacey Beach Day, Ellison Onizuka Day, and many others. The collective effort of each subsystem of Team RoSE has led to the current rover being prepared to successfully complete the 4 missions of the University Rover Challenge.